Okay, so we'll go ahead and look through the last two pages of the calculus review by request. This is actually my second rendition because I actually realized I messed up one of the problems and I messed it up badly enough that I had to start over because it was just too messed up. Very, very small misread, but it made a big difference in the answer. So we'll talk about that when we hit that problem. But that's why you're going to see some of this already filled out. So I'm going to talk my way through problem number 11 a little bit at a time. And hopefully this is going to make sense. I prefer it not to be this way, but I just ran out of copies. So here's what happened. I want to know the growth constant. And so in this problem, we know that if it is some kind of an exponential growth or decay problem, we start here with y equals ce to the kt. That's the place we should always start in calc, and I know that we could do it the chemistry way and say y equals c times 1/2 raised to the t over 27/7. But the reality is this problem asks for that growth constant, and that's specifically tied to this version of the equation. So that's why I wanted to do that. So moving into this idea, I know that whatever C is, when we hit that half-life moment, that 27.7 days, Y, whatever it is, will be half of C. So if it was 100, it'll be 50. If it was 4, it'll be 2, whatever. But when we divide it across, we're just going to get a half. So no matter what happens at 27.7, this value y will be half of c, and therefore when I divide it across, that's what's going to happen. So I take the natural log of both sides, and then as soon as we divide by 27.7, we have this number right here, and we're good to go. We have found the constant. That means it is decaying at a rate of about 2.5% per day, okay? Now, moving on a little bit further, it asked me what that initial amount was. Now, keep in mind, I know that when there was 6 days into the experiment, that was 7.9. So if you look at what we have, we know the time was 6 days. We know K because we found it right here. We know how much it would be at 6 days. We just need C left. And so that's what I did is I just plugged in all the numbers to each of those places. And then, of course, this is just a number I can get on my calculator. And if I take 7.9 and divide it by that number, I would find out that the initial condition was 9.1798 grams. Okay, just fairly straightforward little problem. Now, when they ask me what's going to be left after 10 days, keep in mind, I now am in a position where I have everything. I know what C is. I know what K is. I've got a master formula, and it says what happened after 10 days. So all I did is I plugged in 10 right here. That's all just numbers that I can plug into a calculator. Similarly, by this same exact equation over here, it says, when will there be 1 gram remaining? So I set it equal to 1. I just went ahead and divided both sides by this 9.1 value. And then I get some decimal equals e to this. And take a log of both sides. That's what happened from here to here. I took the log of this side and e disappeared. The log of this side is that. And then a quick division. And I got 88.5 days. Now, one thing that I think that is worthy of note is 85 days is, let's see, 85 days. Was that 85 days? 88 days, excuse me. 88 days is a little bit more than 3 half-lives. So keep in mind, if we have 3 half-lives, it gets cut in half 3 times. But it went a little bit past that. It's 3.17 half-lives, right? So let's see. So it's going to be a little bit more than that. So one thing that is of note is that if I started with 9.179 grams, and I 1 half-life, so 27 days in, 27.7 days in, I'm down to 4.5. 55 point whatever days, 2 half-lives in, I'm down to 2.2. 3 half-lives in, I'm down to 1.1. But then I have even a little bit further to go, so I'm already down to 1.1 grams. So it feels plausible that by the time I go that extra bit, because it was 3.14 half-lives, that extra little bit of a half-life would suck up this last little bit of a gram to get us down to the number 1. So it feels plausible. Because there's a lot of times you just can't check things easily. Now, here's the problem I made a mistake on. So, and it's actually a little deeper into the problem, but I did make a little bit of a boo-boo, and I'm going to fix that. So we have this colony of widgets, and a widget is just a fictitious item. It could be a bicycle, it could be a mug of coffee, it could be a house, it could be anything, but we call it a widget so that if the price of a widget is $5 million, nobody's like, hey, a bicycle's not 5 million. It's just fictitious, so the numbers don't have to mean a whole lot. So this colony of widgets is growing at a rate proportional to the number of widgets it has. So that means dy dt equals ky, or in fact, in this case, it would be d widget dt equals k widget. That's kind of the way the problem is setting, but we should know that that is going to turn us into the CE to the KT kind of problem. So here's what we have. We've got y equals CE to the KT. We know that's our story. And it says, what is the initial population of the widget? And that's because it says after 10 minutes, there was 850. And in the next 5 minutes, it grew to 1200. Well, this was a very silly thing that I did. So I know that in 10 minutes, we had 850. And I don't know what C is, and I don't know what K is. But in an additional 5 minutes, that would be the 15th minute, it grew to 1200. I still don't know C, I still don't know K. Here's where I made a mistake. I just used the number 5. I saw the 5 minutes, I used 5. Then it says the next 5 minutes, which is actually 15 total. Silly mistake. So if I divide these two by each other, this guy divided by this guy, the C's would cancel because when you divide, that's what would happen. E to the 15k divided by e to the 10k would be e to the 5k since you subtract those exponents. And that's going to be 1200 over 850, whatever that is. Now, of course, if we take the natural log of both sides, notice that I'm now repairing my work because I made a little bit of a mistake here. So I'm going to take the natural log of 1200 divided by 850, I should have known better, is 0.344, and divided by 5, I get 0.06. And that honestly makes far more sense than what I had, because clearly the widgets are growing, so K has to be a constant that is positive, and I had a negative constant, and that didn't make sense. I should have realized that I had done something silly. I pays to pay attention. But I was doing this at the end of a very long day, and I was tired, and I just wasn't thinking as clearly. Okay, so then it says the next one. What is the rate of change? Okay, so now we have this nice little formula. I know what K is. Now, I actually don't know what C is yet, but it turns out, oh, actually, I do know what C is, because I could plug it back in. Oh, you see remnants of my first error. It was right here. This should be positive 0.06. So let's see. If we took 850 divided by, let's see, that would be E raised to the 0.0689710. I got 793. So my initial number of widgets should have been 793. So we now have all of the bells and whistles for this particular problem that we want. We have 793.351 widgets. Now, what we could do if we wanted is we have C, we have K, we have T. It says, what is the rate of change of the population? That says, take the derivative and plug in 10. And I could totally do that. But it would be a waste of time because I know something else. I know that the rate of change of the widget population, dy dt or dw dt equals k times y or w. That's the given statement. It actually says that in the story. In fact, I think I'm going to go ahead and do it that way. D widget d time equals k widget. Now, that means d widget d time at that value. Well, I already know that the number of widgets we had was 850, and I know that my K value is 0.0689, And so if I could take that 0.0689 number and multiply it by 850, it should be 58.565, 58.565 widgets per minute. That's how fast it is growing at that particular moment. Now, if I had taken the derivative of my master equation, I would get the same thing. It just would have been a lot more effort because I already have a differential equation that talks about the rate of change of the widgets. So I'm going to stop right there. That's numbers 11 and 12. Okay, and I'll post those and I'll do the other ones in another video.